This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you enjoy the podcast, please follow or subscribe to it wherever you listen to your podcasts. It will help us grow. Today, Percy Liang from Stanford University will tell us about how models like ChatGPT, some call them language models, others call them foundation models, how they're built, what they do on the internals, and how they should be evaluated. It's the future of AI chat. Before we jump into this episode, I want to ask you to rate and review the podcast. It'll help others figure out if they're interested in the future of everything. Everybody knows that in the last year, the world is being turned upside down by language models or foundation models like ChatGPT. These are amazing AI tools that can take questions and apparently generate pretty good answers. But how do they really work? What data was used to train them? What are the hidden biases? And most importantly, how do we evaluate them? And how do we evaluate the companies that produce them or organizations that produce them? Well, Percy Liang is a professor of computer science at Stanford University. He's also a senior fellow at the Stanford Institute for Human-Centered AI, and he runs the Stanford Center for Research on Foundation Models. He's deeply looking at how to build and evaluate these models. So Percy, let's start out. You kind of were instrumental in introducing this phrase foundation model. And a lot of times you're using it the way other people use large language models like ChatGPT and others. So let's start out. What's a foundation model to you, and why was it important to have a different term for these kinds of things?
Yeah, thanks, Russ. So the foundation model is a term that we coined 2 years ago. And 2 years ago is eons in the era of AI. And we thought that there was something big emerging. And people use the term language models. People are using language models for decades. And it meant always a model over language, natural language. So you have a sequence of words or tokens, and you put a probability distribution over these words. But what was happening was that GPT-3 came out, and GPT-3 was a language model, of course. But what we saw was that it was not just language models. It was also vision. It was other modalities. And we've seen, for example, in models over protein sequences. And we felt like language was both not really capturing all the modalities, which we thought were important, but also the term large language models didn't really underscore the importance or the role that these models were going to have. So we called it foundation models because we felt like there was a paradigm shift where we all of a sudden have these huge models trained on broad data, which served as a foundation for developing other products and models downstream. So that's why we call it a foundation model. It's something that you invest a huge amount of capital in, build once, and then now this can be repurposed for many different tasks. In contrast to the previous paradigm where everybody would collect their data, train a model, and deploy it, and there you have these silos. But now we have this, all of a sudden, this centralization. And that's why we figured that it deserved a new name.
Great, and actually that makes a lot of sense. So for people who don't, your work and your group spends a lot of time building these, testing them, and we're going to get to that because even recently you've done some really exciting things in terms of evaluating a whole bunch of language models. But let's go back to some basics. Can you explain to a non-technical person how are these built? What data is used? We always hear about training. So how are they built, and what is the training data that's used?
Yeah, so this is a good question. So anytime you do machine learning or AI these days, there's basically two things. There's the data, and then there's the model architecture. So let's start with the data. So one of the insights which is not new, but I think has gotten a lot of traction lately, is the idea that you can just take as much data from the internet as you possibly can get your hands on, and you can actually make use out of that, right? So in the past, where you would train a question answering system, you would have to have data question answer pairs, for example. Or if you train a a cat versus dog detector, you would have get images of cats and dogs. But the idea that we have this rich resource called the internet, and there's all this data out there, and if you could figure out how to harness that, you would have basically a much more powerful model. So long story short, the data that is collected is generally based on these web scrapes, usually Common Crawl, is a sort of a public domain, scrape of the internet.
And when you say scrape, you mean they literally go to the websites and they collect all that text that's normally displayed in our browser. They take it and they put it in a file to give it to some model architecture that you're going to tell us about in a couple of seconds.
Yeah, that's right. So there's a process. So Common Crawl is an organization that actually produces these, does the scraping.
Okay, Common Crawl
has these. Yeah, and that's one data source. Then there's Wikipedia, which I think everyone knows about. There's also some books, which there's some copyright issues around this, but nonetheless, these sometimes go into the training data. Sometimes you have code from GitHub. You have papers from archive. Maybe there's some other sources, PubMed articles. And so it's basically this sort of hunt for, you go online, what's available, you grab it, and then you form a pretty large data set. So generally the data sets right now are, just to give you a scale of things, are people talk about training on 1 or 2 trillion tokens and a token is maybe 2.5 tokens per word, let's say. So trillions of words, let's say trillions of words. Or tens of trillions of words.
Much more than the average human, or in fact, much more than any human has ever read.
Yeah, much, much more than that. Okay, so you have all this data. And then there is a model architecture, and that just means it's a neural network, which are called a transformer. So the transformer was this thing that was introduced by some Google researchers back in 2017, which again builds on attention mechanisms, which were developed by Yoshua Bengio's group in 2014 or 13. So there's a long history of developing these type of architectures, but the one that seems to be the one that people have converged on, at least for now, is a transformer architecture. I'm not going to go through the details of this, but it's basically a giant neural network, which is takes in a sequence and then does a huge number of matrix multiplications, different operations, and produces vectors, which then could be used to predict future sequences.
These are vectors of numbers.
Yeah, vectors of numbers.
Okay.
And so you train a model, which means this model has often billions of, if not tens or hundreds of billions of parameters. So GPT-3 was 175 billion parameters. And so just as a sort of a goalpost, so we have, let's say, 100 billion parameters, just to give a round number.
And when you say parameter, these are part of the model that when you start off, you don't know what the value should be, but after exposing it to trillions of pieces of text, it then can estimate what those parameters are so that in the future, it'll be able to make predictions. I just want to check.
Yeah, exactly. So a parameter, it just means a number. So you basically have 100 billion numbers that you need to set somehow. Right. You start, all of them are random in the beginning. And then you take your training data, which is, remember, tens of trillions of words, and then you stick it through some algorithm, and it sets these numbers.
Gotcha.
And it sets the numbers based on an objective, and the objective function is to predict the next word. So you're given, let's say, half of a Wikipedia article, and you try to predict the next word. And so this seems very mundane. Right, okay, so predict the next word. But it turns out that predicting the next word is actually encodes a lot, because in order to predict the next word, you have to understand I'll say scare quotes, understand the what's going on in the sentence. For example, if I say Stanford was founded in blank, in order to predict that, you have to know something about Stanford. Or if you
and know that it's going to be a year probably, and that it should be a year that hasn't happened yet, stuff like that.
Yeah. So all of this is actually based on a very simple and elegant principle, which is just predicting the next word. And what's sort of incredible about these foundation models is that once you do this at scale, you can actually have a model that you can now not just predict the next word in a document, but you can give it instructions. You can say, generate a poem in the style of Shakespeare about Russ Altman or the future of everything, and then it will do something. We can try that later.
Right. Well, one quick question. You said based on the previous words, it'll predict the next word. How far back does it look? Like, is it looking at the previous 100 words, 1,000 words? Because it seems to me that might be an important thing to know, but how far?
Yeah, so this is called the context length. And this number has gone up over time. So I think it's gone from, let's say, 1,000 to maybe 10,000, and now people are looking at context lengths of even 100,000 tokens, which so quite a lot. You can fit entire books now into these context windows.
And tell me if I'm wrong, but this seems important, because if the key thing to know in order to get the next word right is 200,000 words ago or 500,000 words ago, and that's not in your context, then you might not get the answer right. I'm asking.
Yeah, so the context length determines the sort of upper bound on how much you can really milk out of the data set.
Right.
Of course, most of the predictions can just be made just looking very locally.
Right.
If I say in the, I'm trying to find a good example, but if I have a word where it's just
like Percy and I are meeting at noon to go have blank.
Yeah.
Lunch is a pretty good guess, and I only said about 20 words.
Yeah, and then after that, it's like a period, which is even easier.
Right.
So there are some cases where you don't need to look very far.
Okay.
But imagine like you're trying to predict what's going to happen in a murder mystery, and it's at the very end, and you're trying to predict who did it. That requires quite a bit of context if it's a good murder mystery.
Gotcha. Okay, so this is really helpful. Okay, so you set it up. You told us about the data. You told us about what that elegant task is. I like the use of that word. Let me ask you a few detailed questions. Well, not so detailed, but we've heard that sometimes these things make things up. The word hallucination has been used. Some people don't like the word. I like the word. When it gets something wrong, what's happening?
So when it gets something wrong, I guess just to frame things a little bit. So these are models that are meant to generate text, which is like the training data. So the key point is that it's trying to generalize from the training data, right? So they shouldn't only generate things which are exactly training data, because then there would be no learning. And now, if you just give a model just token sequences, there's no notion of truth. There's no grounding there. And in some cases, this is actually fine. If I wanted to generate a fictional story of someone, then actually,
there's no wrong in fiction.
There's no wrong thing. So I would push back on saying that the hallucinations in itself is fundamentally bad, and we want these models to only generate things which are factual, because the notion of facts is also a little bit hazy. Now, in a given application, there turns out to be things that you should say, and things that, by you, I mean the language model should output, and things that the language model should not output, right? So if I ask a biomedical question, and I say, okay, answer truthfully from this data source, then there are things that it should just not, it shouldn't make up things. Right. It can suggest if there's uncertainty, maybe it can suggest options, but it shouldn't just confidently make up things. Whereas in the context of generate me a play with about dogs and GPT-3, then maybe it's fine if it just makes things up. So I think this is the root of the way I see it is there's an element of creativity, of creating things which are novel. And that's the underlying mechanism which is tied to generalization. This either produces undesired hallucinations or creative things. And what's needed is on top of that a way to control for what you want and what you don't want. And so one thing I didn't mention, but is actually extremely important. So I lied a little bit when I said I hallucinated a little bit when I said
we humans can do this every now and then.
I said that it's just predicting the next word. That's the first step of training. The second step is now it's called alignment. In some people call alignment. Some people use the term reinforcement learning from human feedback. And the point of this is now we have just raw potential. You can have the base language model is just someone who's so just to draw an analogy, so creative. Now you need to sort of put a little bit of a lid on. Okay, let's put you in line. You're gonna follow. If I'm gonna give you instructions, you're gonna follow in this way. You're gonna be polite. You're gonna not lie. You're gonna not generate racist or toxic content. And that alignment happens generally on top of the base model training.
That's fascinating.
And that's where a lot of the hallucinations get kind of driven down.
So it's a separate. So there's the pure or the elegant, like predict the next word, but then as an engineer, you add other constraints basically on the output. Is it that you tell it to change its output, or do you just throw away the output and ask it to try again?
So the typical algorithm I just described, reinforcement from human feedback, is you train a model, and then you give it some instructions, and then you ask it to generate a few options. And then you go to a human and say, Russ, which do you like better, A or B? And then you say A, and that says, okay, well, let's make the model generate A more and B less. And I go to you again and say A or B.
Okay.
And you do that over and over again. It'll be a team of people who are providing feedback. And then through that refinement process, that's where a lot of the behavior of the model gets determined.
And I'm guessing there are a whole bunch of parameters for those models as well. In addition to the parameters that were set up for predicting the next word,
Actually, this is important to clarify. It's the same model. Same model, you just change the weights.
Gotcha.
Based on this new objective, which is to favor A over B as opposed to predicting the next word.
Very good. So very good. Yeah. That's very helpful. This is The Future of Everything with Russ Altman. More with Percy Liang next. Welcome back to The Future of Everything. I'm Russ Altman, and I'm speaking with Percy Liang from Stanford University. In the last segment, Percy gave us the basics of how foundation models work. In the next segment, he will tell us that it's absolutely critical that we evaluate these models and that we evaluate the organizations that put them out. Percy, I wanted to move to how do we evaluate these? How do we know which ones are good, which ones are bad? Or, I mean, is that even the question? And I know you've done a lot of work in this area. So how do you think about the evaluation of these foundation models?
Yeah, evaluation is really, really tricky now. Before these foundation models, often we have data sets, like question answering data set, machine translation data sets, image classification data sets, which would be well-defined tasks that researchers would go and work on. Like examples include like ImageNet and Squad. Now the paradigm has changed, right? We don't work on necessarily tasks per se, but we have this general model, and now it's sort of everything's flipped around. Now we have this model, it can do things. Now we have to figure out what it can do, as opposed to saying, we want to do this, go build.
Right, and you could imagine that any given model might be good at some things and less good at other things. So good or bad is not really the question. So how do you wrap your head around this?
So we've been grappling with this for the last 2 years or so. The thing that we have done at the Center for Research on Foundation Models is we put out a benchmark called Helm, which stands for Holistic Evaluation of Language Models. And it tries as much as possible to cover everything. Of course, everything is a lot, so we're not covering everything, but we try to have representative prototypes to cover all the different aspects. So the way we think about it is there are a set of potential use cases or scenarios in which these models will be deployed. Maybe for text classification, maybe for summarization, maybe for question answering. And then, so we have about 40 different scenarios, which we've kind of sourced from the existing literature, looking at how these models are actually used in industry and so on. And then for each of these scenarios, we look at what do we care about that. And typically people are interested in accuracy. That's the go-to metric. But we thought that this is not the end all be all. Accuracy is important, but we also care about calibration, which is a measure of how well a model knows what it doesn't know. And it turns out the models actually are confidently wrong a lot of the time as they get more accurate. They also get more incorrectly confident.
I know people like that, but that's a different podcast.
Yeah. Then there's a robustness to different typos. There's bias, there's toxicity, and there's efficiency. So we look at all these different metrics in the context of these scenarios. And then we go around and find all the models we can get a hold of above a certain level of capability. And in the end, we had about 30 different models. We evaluated the giant cross product of all of these, and we made this all available on our website for future analysis. So this was at the time, so this was December 2022 when we released it, the most comprehensive evaluation of language models. And over time, we've been trying to update this with as new models come out, as we discover new use cases, and so on and so forth.
Are the companies happy to share their models? Like I can imagine it's somewhat risky because they don't know how they're going to perform and they don't want to get like bad marks. So how open have the companies been about providing you with their models for testing?
So most of the models we evaluated are public because the company, that's their product. They put the model out as an API. So in some ways, they don't have a choice. There were a few cases where we did collaborate with companies. And overall, companies, I would say, have been pretty supportive of the project because I think, in general, everyone wants to figure out how well the models are doing. But there is a sense in which we want to, obviously, companies want their models to look good. So that's the sort of the evaluation. It's really, I would want to stress, an ongoing challenge to keep up with the latest models and the capabilities and trying to evaluate everything. I just want to maybe point out one, give people a sense of how difficult evaluation is. If you think about a single example in a data set could be, write me a well-researched article about World War II and its implications for the coming century. And models can now generate a whole essay, right? How do you evaluate this? It's basically what you would do in school.
Yeah, this is what you have history professors for.
An essay, or even in other domains like in law or in medicine, where you're asking a model to do something complicated. Now you need a doctor or a lawyer to evaluate that. So even evaluating a single data point, if you did it properly, could take like an hour for a person. And so this is it's not machine learning classifies this image. It's a cat or a dog, right? We're far beyond that level.
Are most of the Helm outputs, are they mostly numerical, or is there anything that approximates a qualitative evaluation?
So most of the ones that we initially worked on are fairly cut and dry, or try to be cut and dry in terms of multiple choice questions. There's a few short answers. We did have summarization as well, which required humans to look at the summaries, which was
expensive, I'm guessing.
Took a bit of, that was expensive. There's been quite a bit of interest in trying to use the model to evaluate the model itself, which we've there's a collaboration with Tatsu and Hashimoto and Carlos Gestrin on alpaca eval, which you have the model rate, the model predictions, and this actually gives you some signal. Of course, you might be a little bit concerned. There's some bias there, and so that's something to be figured out.
Now, you've also done, recently, you've just announced kind of a scorecard. Tell me what motivated that and how that works.
Yeah, so this is, I think you're referring to the Foundation Models Transparency Index. So the story behind this was we were thinking about model evaluation as a way to ground the conversation of where we are as a field, what these models can and can't do, and how to evaluate the risks and also the opportunities. But then if you think about from a responsible AI perspective, right? We want to develop models and to benefit society or yada, yada. What does that actually mean? So initially we thought about how do we measure responsibility? And this is not a property of just the model, but it's about how you produce the model and how you deploy the model. And it's important we focus a lot on, ChatGPT is an artifact or Claude is an artifact, but it's important to remember the whole ecosystem where there are people producing data that get used to train this model, and then that model is deployed in various products, and this is how it has downstream applications. So you think about the social impact, you need to look at the whole ecosystem. So as we were doing that, we realized we have no idea what's going on in the ecosystem because companies aren't too forthcoming with the details. So then we decided, well, the first step for responsibility is you need some transparency. And transparency has a long history of being useful as just a general good measure. For example, you think of nutrition labels and in other fields. So we decided to evaluate not models, but organizations based on their transparency practices. So we have 100 different indicators covering quite a big span from, did the organization disclose the labor practices for curating the data? Did they disclose the data sources? Did they disclose the compute used? Did they do model evaluations for capabilities, show limitations? Did they talk about mitigation? Did they disclose the usage policy? Do they have usage policies for how their models can be used? Did they all the way to if there's a problem that a user has, is there a reporting mechanism to say that something went wrong? So it's pretty expansive, and we evaluate 10 different organizations based on these 100 different indicators. So everyone gets a score out of 100, and the top score was 54. So, not I guess in a classroom setting,
that's not very good. That's not very good.
That's not very good.
Yes. So that really, we have to pause a moment and think about this. Okay, so this is the best score, and how bad or how low did the scores go?
They go down to the tens. And I should say, I don't want to be too negative here. I think this was really the first. It was like a pop quiz. People didn't see this coming, but if you look at what we're trying to measure, many of these things, I think companies can absolutely do. And many of these things are actually aligned with business interests, like having better documentation for the APIs, having better evaluations. Some things are maybe not so much, like people aren't going to suddenly reveal all their proprietary secrets about what data they use to train on. But many of them, I think companies could easily improve on. So the hope is that now we have anchored transparency, which is a very fuzzy, abstract concept, into raw numbers. We can track how this evolves over time. Maybe next year, the organizations will hopefully do better as a result of having these numbers stare them in the face.
How did the companies respond to this pop quiz? Were they irritated, or like Helm, did they say, no, in the long term, this is probably a good thing?
I would say the amount of irritation was higher for the transparency index than for Helm, for sure.
Yeah. Okay. I think we can all imagine why. And I know that my students don't like pop quizzes, and I could imagine that the companies didn't like the pop quiz, and yet it might be good for them. And that's exactly what I tell my students. Let me just ask, let's close. There's this idea that many of these models are closed. Like we don't have full, as you just described, we don't have full insight into lots of things about how they were built and how they're being used. And then there are open models, which you have pioneered yourself, where you make perfectly and publicly available what the data was that you used to train, how the architecture works. Can we end up with just a little discussion about the costs and benefits of open versus closed systems and how you're thinking about those trade-offs?
Yeah, this is actually a very much an ongoing discussion about the benefits and risks of open versus closed. First, I'll say that it's a spectrum between open and closed. Often when people refer to open, it means that the weights of the model are widely available. And I'll talk a little bit more about what the implication of that is. As opposed to closed, which means that the models are available, but only through an API access. You can query the model with inputs.
Pretty much the
outputs,
archetypal black box.
Just take the model. Yeah, exactly. So what are the benefits of open models? Having weights gives you downstream users and developers just a better notion of, okay, what are you dealing with? Here, this is the model. I can inspect it. There's also another spectrum here, which is that it would be better to have more description of how the model, how these weights came about, also the training data. So some models, like Eleuther AI is an organization that produces models. All their data, all their code and the models are fully open. That's one end of the spectrum. Meta produces the Llama models, which are probably one of the best open models out there. The weights are open and they're available, but the data is not. So that's somewhat open. And then there's now you jump over the line to the API providers. So the benefits are open are that you can have more transparency over what you're actually running. You can extend it more easily because you can fine tune, you can customize in various ways that you can't when you're just have a black box API. It's really you're at the whim of whoever's defining the API and what kind of access they give you. And there's more flexibility for you. You can run it in your local hardware, which could be beneficial for privacy as well. So those are the benefits of openness. So there is maybe the benefits of closed is that you have greater control, in particular against potential misuse. So you can say, we don't want people to use this model to generate disinformation. And in principle, you can monitor that and try to prevent
you described a little
from
bit about that when you were talking about the reinforcement learning, and I like these kinds of answers. I don't like this. Don't do toxic things, etc.
Yeah. You can have greater control, although it's more nuanced than we have really time to cover, because these closed models can also be jailbroken, which means that you can devise clever prompts, inputs that you can feed them.
Yes, I was going to
bypass
ask you
the
if closed
safety,
models were more
filters.
secure in some way, because if it's inspectable, if the open models are inspectable, they could be inspected by people with nefarious goals, whereas a closed model might be a little bit harder to kind of use for bad purposes. But I think what you just told me is, even in that case, people have figured out ways to kind of get around the security.
Yeah, you can circumvent it, and some of the APIs allow you to fine tune, and people have shown that it's very easy to just fine tune and break the safety. So this is very much an ongoing debate. I would say one thing that in favor of open models and security is that if you think about how computer security works, all the cryptographic protocols and all the source code is open source. OpenSSL is open, right? And this is crucial for security because it allows the whole world to inspect in broad daylight, here's the security mechanism, and to find vulnerabilities and make sure that we're doing, we're all looking at each other in the eye and say, okay, this is what security means, okay? And one of the lessons from computer security is that so-called security by obscurity doesn't work, right? If you say, I'm going to be so secure, but I'm not going to tell you what I'm doing, it turns out that a determined enough bad actor can reverse engineer, figure out, or there's a leak or something, and then it's actually less secure than if you're just more open about what your security practices are. Now, in the models case, it's not the same because they're models, not code. But some of these principles, I think, still carry over.
Thanks to Percy Liang. That was the future of AI chat. You have been listening to The Future of Everything with Russ Altman. If you enjoy the podcast, please rate and review it. Also, remember to follow it so you can hear about new episodes and you'll never be surprised by the future of anything. You can follow me on Twitter or X at @RBAltman, on Threads at Russ B. Altman, and you can follow Stanford Engineering at Stanford ENG.